Hello, welcome to the lecture series on vehicle dynamics. Now we will talk about steady state handling. In this session, in the part 1, the first video, I will explain steady state handling and I develop cornering equations. In the second part of the video, we'll discuss about suspension effects on cornering, then transient handling, and also we will discuss about various vehicle dynamic tests. So, handling is to do with maneuvering. So, I am talking about vehicle maneuvering. This is what we call it as the handling part of it. Okay, this we have explained earlier in the definition stage. Let us study the mechanisms involved in this. Also, first thing is I have explained Ackerman steering principle. Most important point is that whenever you are taking a turn, the perpendiculars drawn to the vertical planes of the tires at the center must all meet at one point. That means when they are taking a turn, these wheels have to trace concentric circles. Another very important thing is that the inner tire should stay larger than the outer one. That is, delta I must be greater than delta naught. This we have understood. Next thing is, what are those values? Delta I from the geometric relationship, you can write like this, where L is the wheelbase length, R is the radius of turn, and the T is track width. So for delta naught, it is L divided by R plus T by 2. Average L by R. So to convert this into degrees, this in radians, to convert this into degrees, pi radians is 180 degree. 1 radian is 180 by pi. That is, this value will be 57.3 you get. So in degrees, delta average is 57.3 L by R. Okay, right. First, let us talk about low speed turning. Means you have a turning like this. The vehicle will enter this turn and with a very low speed it will be turning. What is its effect? Let us see. That is, low speed turning means to say complete absence of centrifugal forces, right? That is what we mean by low speed turning. We neglect low speed turning means we neglect centrifugal forces acting on the vehicle. Steering is normally affected by changing the heading of the front wheels. During turn, all tires should be in pure rolling without lateral sliding because there is no centrifugal force. To satisfy pure rolling, the wheels should follow curved paths with different radii originating from a common turn center. Okay. So the terms Ackerman or Ackerman geometry are often used to denote the exact geometry of the front wheels. The correct angles are dependent on the wheelbase of the vehicle and the angle of turn. The other significant aspect of low speed turning is the off tracking that occurs at the rear wheels. So that is the disadvantage. What is that off track? Look here. This is the intended path of the vehicle. Sorry. Intended path of the vehicle. In low speed turning, the front wheels will follow this path. The rear wheels will not follow this path. Instead of that, they trace this path. Okay, this distance is what we call it as off tracking. Off tracking. How do we find off tracking? This length is R. Okay, this is R into this distance is R cos L by R. R cos L by R. So the difference is R minus R cos L by R. You see here, you can see here R is the distance and L is the wheelbase length. Okay, so now the thing is, suppose you want to find what is the radius of that. Okay, R cos L by R. Suppose if you take this point, correct? No. But what is this going to be? This is a triangle. This length is L. This is R. This angle is say theta. Okay, R cos theta. Theta is nothing but L by R. Okay, that's what you get. So delta is R minus R cos L by R. So let us expand this using cos series. R, this is 1 minus, this is expansion of cos series. Let us ignore higher order terms. Then approximately delta is equal to L squared by 2R you get. So this value is approximately L squared by 2R. That means if the wheelbase length is very large, off tracking will be very high. And moreover, if R is small, it will be very big problem. So this is a problem that is faced with most of the long wheelbase vehicles, particularly trucks. Okay, so let us see now. So you can see now how exactly the rear wheels will be off tracking. Okay. So that is a difficulty we come across with the low speed vehicles because of the absence of centrifugal force. So here there are many videos available which explain vehicle handling. So you can play and learn those things. And there's a very interesting video that is will explain various driving tricks. These are available on the YouTube. Okay, so you can just watch these videos. Very interesting, very creative. Let us look at steady state handling. What is steady state handling? So steady state handling performance is concerned with the directional behavior of a vehicle during a turn under non-time varying conditions. How exactly a vehicle behaves while taking a turn under non-time varying conditions. Means to say, vehicle will be negotiating a curve of certain radius, that is constant radius, at a constant forward velocity. So the forward speed is constant, the radius is constant. That is what we mean by non-time varying conditions. So it is something like this. Constant radius with constant forward speed, it will be taking a turn. That is what we mean by steady state handling. Okay, all right. So since we are talking about steady state handling behavior, we will not consider inertia properties of the vehicle. Okay, that's the main thing. So the problem becomes much simpler. So I mentioned about high speed cornering and low speed cornering, and problem associated with low speed cornering, that is off tracking. Now let us talk about high speed cornering. Means to say, we will consider centrifugal force. Earlier we had ignored centrifugal force. So when a vehicle is negotiating a turn at moderate or higher speeds, the effect of the centrifugal force acting at the center of gravity of the vehicle is to be considered. Okay, earlier we had ignored this. That is in the low speed cornering. So moment there is a centrifugal force, I think a number of times as mentioned is, the tires must develop appropriate cornering forces. Correct, no? Centrifugal force, appropriate cornering forces. So if this is what the vehicle model is, vehicle model is. So this vehicle is taking a turn, let us say like this. So then the centrifugal force will be acting this way. So that time, to resist these centrifugal forces, you will get this forces over here, right? Those lateral forces. So to balance the centrifugal, the tire must develop appropriate cornering forces. These are cornering forces. So when a vehicle, these side force acting on a tire produces a side slip angle. So I'll show you in the next slide. So suppose if you have on this tire a side force, then there is going to be side slip angle. So I'll show you there later. Earlier also I explained tire slip angle. So we represent this by alpha. When a vehicle is negotiating a turn at moderate or higher speed, the four tires will develop appropriate slip angles. This is the one. The handling characteristic of the vehicle depend to a great extent on the relationship between slip angles of the front and the rear tires. That's very important. Here also you'll get slip angle, here also you'll get slip angle, here you get. Correct. Now you can call this as alpha F, here you can call it as alpha rear. So the relationship between alpha F and alpha R are very, very important. So you can see here, when the vehicle is taking a turn like this, you see, you will get the vertical force here. You know, this is the inner side, there is the outer side. The load on the outer wheel is high, that's why you can see this vector is quite long and this vector is small compared to this because less load, and you will get the side force. Correct. The side force. These side force will create the tire slip angle alpha F here for this alpha R, like this. Okay, maybe this angle is smaller than this angle because this side force is less than this side force. Okay. So this is what exactly I explained. Now you can see here is the side force acting. The tire carcass will take a shape like this. If it is not squirming like this, then it is supposed to roll in this direction. Because of this, it is rolling in this direction. This is what I call it as tire slip angle. This happens because of side force acting on that. When a vehicle is negotiating a turn at moderate or higher speed, the four tires will develop appropriate slip angles. The handling characteristics of the vehicle depend to a great extent on the. So whatever I repeat, I think the same thing has been repeated here. Okay. Now you see here. This is what I told you about this. I shown you also. Yes. So how it all depends on the side forces, what slip angle they create. Based on that, the vehicle behavior depends. Now let us define now cornering stiffness. So here Fy is the lateral force that is acting, alpha is the tire slip angle. This ratio we call it as cornering stiffness of the tire. So you see here there is lateral force here, Fy, slip angle alpha, drawn this characteristic. The slope will give you the C alpha, cornering stiffness. Up to certain angle, certain slip angle, the relationship will be linear. Further lateral force if we apply, probably the lateral force with the standing capability will come down. Correct? It is better to use well within this linear range. What are the cornering stiffness, the factors that affect cornering stiffness? Here cornering stiffness versus inflation pressure is given. This characteristic has been drawn for radial tire, this has been drawn for bias ply tire. So it's clear at a given inflation pressure, let us say 32 bar psi, sorry 32 psi. For a radial tire, cornering stiffness is high compared to bias ply. Okay, so it is better. The radial tire will offer a better resistance. So that means we can take a turn at much higher velocity if you use a radial tire compared to bias ply tire. Now let us look at aspect ratio. Aspect ratio is at height by width. This is what we call it as aspect ratio. So now 60 aspect ratio let us take. This is 60 aspect ratio. This is also 60 aspect ratio. Sorry, this is 60 aspect ratio, this is 70 aspect ratio. If the aspect ratio is low, aspect ratio is low value, the cornering stiffness will be better. So if you see the racing vehicles or high performance vehicle, or you can say high performance vehicle, so this will have what you can say very low aspect ratio, so they perform better. And the rim size is bigger, it's better. Okay, rim size bigger, better. Smaller aspect ratio, it's better. So here again cornering stiffness for tire size designation, aspect ratio. So a lower aspect ratio tire is better than a higher aspect ratio tire. So you see here now lateral force by vertical load. So this is what you can call it as slip angle. As the slip angle increases, lateral force will also increase. Here's cornering coefficient versus percentage of rated load. Cornering coefficient is defined like this. Cornering stiffness per unit of vertical force. So these are very important while choosing type of tire. Okay, very important. Please note this. Now let us develop cornering equation. For that we'll model this car. This model you can call it as bicycle model. Here The rear two I have put them together, got a single wheel. Front two I have put them together, got a single wheel. The center of gravity is here and is the turning radius. This value is B and this value is C. So it is B and this is C. Okay, lateral force at the front and is lateral force at the rear. Okay, now let us the steering angle. Let us develop an equation for steering angle. First, simply draw a vertical line like this. Then let us draw this line here. Then let us draw this line here. Okay. Right, sir. Now this line here. So the angle between this line and this line, this blue line and this blue line is 57.3 L by R. Neutral steering. Okay. But what is that? We have steered delta. Delta is steered. Between this and the angle, you should have steered whatever we have. This tie slip angle is, you should have gone here. It's going like this. So alpha F. And this steer angle is alpha R. Is that okay? So from here, what is that we can write? We can write what is delta equal to. So delta equal to this 57.3 L by R plus alpha F. Correct? Then this will give you this much angle. I want to find delta. In that I have to subtract this much angle, alpha R. So 57.3 L by R plus alpha F minus alpha R. Okay. Now let us find this alpha F and alpha R values. So centrifugal force at the front. What is this? Front load. That is WG C by L. Front load M V squared by R. And this is nothing but static load. So WF by this one, WC by L. Correct now? That is the load, WF by G, mass, V squared by R. Similarly for the rear, this is the load. Our definition is C alpha F is equal to FYF by alpha F. So alpha F is equal to this divided by this. So FYF is nothing but this value, alpha F. You will get this. Similarly, alpha R, you get this. Then we will substitute into this equation. I will get this one. V squared by GR. So now this part you call it as K. This K is called understeer gradient and V squared by GR is lateral acceleration. K is understeer gradient, AY is lateral acceleration. This is what we call it as cornering equation. So now K is this. If the load on the front is, assuming C alpha F and C alpha R are same, for the front and rear tire, if WF is greater than WR, K becomes positive. If both are equal, K is equal to 0. If this is greater than this, then K is negative. Correct. Now delta is equal to 57.3 L by R plus KAY. K positive means delta you have to steer more than 57.3 L by R. Then that case is understeer case. Understeered. 0 means exactly 57.3, then it is neutral steer. K negative means you have to subtract less than what you require, oversteer. So vehicle steers more than what is required, that is oversteer. It steers less than what is required, then it is understeer. Exactly the same, then neutral steer. What is the physical interpretations of this? Neutral steer, understeer, oversteer. So K equal to 0, I said these two are equal, alpha F is equal to alpha R, delta is equal to 57.3 L by R. That means all the four wheels rotate about this point. If this is greater than this, that is K is positive, alpha F is greater than alpha R, it demands more turning radius. You want to maintain the same delta. Otherwise, you want to turn about the same point means you have to turn the vehicle more. This extra angle you have to turn. Correct? That extra angle you have to turn. That is what alpha F. Right, sir. And now, if this is less than this, K is negative, then you see here. It will start turning over here itself. Should have turned here. To bring this point back to this, you see here, this has to be brought back. Okay? If you bring back this point, then this point will stretch to this point. So it will have a very short turning radius. This requires a long turning radius. So in simple words, don't get confused. Delta is equal to 57.3 is what theoretical value is. If your vehicle is an understeered vehicle, you have to steer more than this. If your vehicle is oversteered, you have to steer less than this, so that it will follow that point. That's the meaning of that. So let me explain further what really the problem is. Suppose this is the vehicle. Right. This is the vehicle. It is taking a turn like this. This is what we want, 57.3 L by R. If it is an understeered vehicle, it will steer like this. it's too much understeered, it's a problem. It will go like this. Okay, it is understeered. That means you have to keep this on the track. You need to turn more. Oversteered in the sense it is like this. It will turn like this. It will turn like this. Is it okay? Now sometimes it might even turn on its own like this. You have to do it in the opposite direction. Take it backwards. Okay? Right. It this way. So you have to counter steer in this case. Or steer less than what is necessary. That's the meaning of oversteer. Right, sir. Now steer angle with speed. Let us say delta is equal to 57.3 L by R plus K V squared by RG. If K is equal to 0, it doesn't depend upon vehicle speed at all. Sometimes this symbol, you better take this symbol as capital V. Whatever the vehicle speed, this is neutral steer. If V is positive, you see, sorry, K is positive, means understeer vehicle. The delta value, as the velocity increases, it keeps on increasing. Means you want to take a turn at high velocity. It's an understeered vehicle. You want to take a turn with high velocity. It's very, very difficult. Look here. This is the kind of angle. It keeps on increasing. At a particular speed, it becomes twice this value. That's corresponding speed, I can call it as characteristic speed. In the other case, if K is negative, as the velocity increases, this value delta may become 0. You do not have to steer. That speed, we call it as critical speed. On its own, it will turn. Okay? Right. So, that's what happens at a very high speed. So this is the character. So it's for the oversteered vehicle. This is for the understeered vehicle. You do not have to steer. On its own, it will steer. That is what really happens. So this concept we call it as characteristic speed, and this we call it as critical speed. So what is that characteristic speed value? In place of delta, 2 times 57.3 L by R you substitute. Correct? No. 57.3 L by R. So now 2 times of that, in that you subtract, you will get 1 time left. AY is nothing but V squared by GR. From that we can find characteristic speed. You know wheelbase length, understeer gradient, you know, G, you know, then we can find out. by characteristic speed. Critical speed means where delta becomes completely zero. Correct. Now KAY 57.3 L by R. So this is the critical speed. So you should be careful. We should never reach to this critical speed. It makes the vehicle unstable. So the primary factors controlling the steady state handling characteristic of a vehicle are the weight distribution of the vehicle and cornering stiffness of the tires. A front engine front wheel drive vehicle with a large portion of the vehicle weight on the front tires may tend to exhibit understeer behavior. A rear engine rear wheel drive car with a large portion of the vehicle weight on the rear tires may tend to have oversteer characteristics. Changes in the load distribution will alter the handling characteristic of a vehicle. It is necessary to choose right type of tire to have right handling characteristics. Before that, I would like to make one more comment. You consider this is the vehicle. And this is the vehicle center of gravity. Let us say this portion, we call it as WF. And this portion, let us call it as WR. Now, there is centrifugal force if it is taking turn here. Centrifugal force of this WF by G V squared by R. And this center of gravity is here, WR by G V squared by R. If this is higher than this, vehicle try to swell like this. That creates understeering tendency. If this is greater than this, then this will try to create oversteering tendency. That's the meaning of that. Okay, right. Steady state response to steering input. There are three outputs here: yaw velocity, lateral acceleration, radius of curvature. Three outputs, and steering angle is the input. During a turning maneuver, the steer angle induced by the driver can be considered as input of the system, and the motion variables of the vehicle such as yaw velocity, lateral acceleration, and curvature may be regarded as outputs. Correct? It has to yaw while taking a turn, and there will be a lateral acceleration. Correct. Also, it has to negotiate a curvature. So the ratio of yaw velocity to steering angle, you can call it as yaw gain. Lateral acceleration to steering input, you can call it as lateral gain. Curvature to the steering input. Okay, this is another response output we can look at. So lateral acceleration gain, you can see here, For AY, it is V squared by GR. For delta, it is 57.3 L by R plus K AY. That is the equation we have. Reorganize this, you are going to get this value. If K is equal to 0, okay, fine, this is the value. K is positive, denominator will be larger than 1. This becomes smaller. AY by delta will be less than, correct, no? 1, whatever it is. AY by delta for K positive. AY by delta will be more than 1 if K is negative. Correct? Lateral acceleration gain decreases with this. Here it increases. So when K is positive, the gain is diminished by the second term in the denominator and is always less than that of the neutral state angle. Finally, when K is negative, the second term in the denominator subtracts from 1, increasing the lateral acceleration gain. Yaw velocity gain. Yaw velocity we have defined like this, and delta we know. Correct. So you write 57.3 V by R. Delta is equal to 57.3 L by R plus K V squared by GR. So then simplifying, you will get like this. Okay, if K is positive, this becomes larger now. Then you will get this. K is negative, then you will get these characteristics with vehicle speed V. Correct? So characteristic speed, you know where it becomes twice, and critical speed where delta becomes 0. Correct? That is yaw velocity gain. With oversteer vehicle, yawing is the issue. Curvature, again for 1 by R, then for delta you substitute, you will get this. Again K negative, this will increase. K positive, this will decrease. Okay, fine. Then there is side slip angle. When your vehicle is taking a turn, if there is no lateral centrifugal force, it is a low speed turning, there will not be centrifugal force, and as I explained earlier, the vehicle interacts like this. Okay, that's fine. And this is what we call it as beta side slip angle. If it is taking a turn with high velocity, then there is centrifugal force, then the wheel outtracks like this. High speed turning. Correct? Beta we call it as side slip angle. Okay. Next, direction stability. 1 minute. Now you take this part of the equation. conditions for stability, that must be positive value. Right? This has to be positive, means the vehicle will be stable only when velocity is this, if k is negative. So if velocity is this value, then only this equation gets satisfied. That is less than the critical velocity. We have proved critical velocity is equal to how much? So that is what? Lg by k. Lg by k only. Only thing is, here I have not written 57.3. It's in radians. So to want to convert into degrees, you can do so. Right, sir? Right, fine. What is static margin? This is x-axis, you know, this is z-axis. Okay. Sorry. So this is x, this is z. So it is xz plane I have taken. So take a point on this xz plane. Correct. You put a lateral force. Okay. The vehicle only slides. It will not yaw. Right? Vehicle only will move like this. It will not yaw. So like that, you take another point, another point, another point like this. These are the points only vehicle will slide, it will not yaw. So join all these points together. This you call it as a neutral stair line. That should be done on xz plane. And you know this is the center of gravity. And the neutral stair point, what is the distance you measure? That is E. This E by L, I call it a static margin. Okay. Now, when the point is beyond, see, the static margin is defined as the distance of the neutral stair points fall beyond the center of gravity normalized by the wheelbase. When the point is beyond the center of gravity, the static margin is positive. It's a positive static margin. And the vehicle is understeer. Vehicle understeers. Anywhere. Right? You apply here lateral load, vehicle understeers. Here if you do, it will oversteer. At the center of gravity, the margin is 0 and the vehicle is neutral steer. Okay, when the ahead of the center of gravity, the vehicle is oversteer. Okay, if it is beyond this, it is understeer. Here it is oversteer. Okay. Okay, this is, we have studied about steady state handling. Basically, we have considered the mass distribution of the vehicle. Based on that, whenever it is taking a turn, what's the lateral force that is acting? And because of that, the tire slip angle gets created. Based on that, we have discussed that whether the vehicle can be an understeer or oversteer vehicle. Also, influence of the tire properties on making the vehicle understeer or oversteer. These kind of things we have discussed. But there are many factors which make the vehicle make which make the vehicle understeer or oversteer. You must look at the tire alignment angles. Tire alignment angles like camber. Okay, even caster. Then also we must look at roll moment distribution. Roll moment distribution. And like that, there are many important things like, roll moment distribution, camber change, lateral force compliance here, aligning torque, tractive forces, all these things, they also affect cornering. That we will discuss in the next session. Till now, thank you.